Today we're talking about nuclear magnetic resonance spectroscopy, or NMR. That's a lot of words for something that you might not have any idea why it might be useful. So let's think about why this might be important, and then we'll get into how it works. The basic idea is we have 5 major types of information that we can get from spectroscopy. We already talked about UV vis. UV vis is mostly active in the aromatic region or in other highly conjugated systems. So we talked about how more conjugation can shift that to the red. We also can use IR. We talked about how those types of spectra can be useful for talking about functional groups. So in the reaction that's shown above, we might see the CO stretch on the left, but we probably also see a CO stretch on the right. And since it's an aldehyde versus ketone, they're both conjugated, we might not see a ton that's different. We might see an OH stretch as well, though. And so we have some amount of clarity from the IR. The NMR is a complementary technique to that. NMR can tell us a little bit about where hydrogens are on a molecule and what the carbon skeleton looks like. And so we'll see different types of peaks for hydrogens that are on the aromatic and different types that are on aldehyde and different types that are on the alcohol. And those differences in both location and number of peaks can tell us about whether we have the right product or not. We can also do NMR to tell us about carbons in addition to hydrogens. And those carbons will all have different signals depending on the environment they're in. We'll talk about mass spec later in this semester, which is our 5th kind of orthogonal way of looking at molecules and getting information from them. Our NMR then takes that radio frequency range and probes it to see what types of transitions we have in that range. Every single nucleus will have a standard signal for each magnet strength if it has a spin. And so for proton NMR, we might have a standard signal that's around 60 megahertz. That's the signal for our instrument. Any individual atom will give a shifted signal based on its environment. And so if we have less electron density around a nucleus, we might actually see that shift to a higher signal. And that move gives us a pattern that's distinctive of that particular molecule and the types of chemical environments that it's in. We know that any individual instrument will have a standard signal for each nucleus that we're looking at. So for our instrument, the standard signal for a proton is 60 megahertz. The instrument that's shown in this picture is a 900 megahertz instrument, which would mean the standard signal for a proton is 900 megahertz. Our instrument costs probably about $25,000 or so, and the instrument that's shown probably cost, several years ago, $1 million easily, and probably several $1 million. So one of my favorite quotes from the instrumental chemistry textbook is, "High resolution NMR are not inexpensive." It's a pretty big understatement, but even so, these are kind of standard in most laboratories. Most instruments today are high resolution Fourier transfer NMRs, including ours, which means that they measure all the signal at once and then they use math to try to deconvolute the signals. So our discussion is going to be centered on this type of NMR. So let's hone in a little bit on that difference in energy that's coming from spin. That difference in energy is going to be a factor of a couple of things. The first of those is a gyromagnetic ratio, which is given by gamma here. That's a property that's distinct for each nucleus. And so we'd say like a proton might have a given gyromagnetic ratio. So you can see at the bottom, the proton gyromagnetic ratio is 2.6512 times 10 to the 8th inverse Teslas inverse seconds. Then we also would multiply by Planck's constant, right, as we often do in this type of equation where we're converting energy and some sort of frequency. And we'd also multiply by the magnetic field. So the stronger the magnet, the more difference in energy you can see. And so you can see why there's a difference in the cost of the instruments. Our instrument generates a small difference in energy. And so it's a 60 megahertz NMR. It has a much weaker magnetic field. The larger instrument, the 900 megahertz instrument, is going to have a much stronger magnetic field. Instruments that are larger than about 100 megahertz have to be supercooled, and so they're typically cooled by helium, which is then cooled by liquid nitrogen. So if you heard about any of the helium shortages recently, you'd recognize how expensive it can be to run some of these more expensive instruments. So like we were saying before, we could have a wide range of instruments. We have 3 instruments shown here. The instrument shown on the left is an old version of 60 megahertz NMR. We have a much nicer one now, but we actually have this old one still in the room connected to the OChem lab. That 60 megahertz NMR probably cost, for a really inexpensive one, 10,000, but you'd go up to 40,000 or even 80,000 for a 60 megahertz NMR. 600 megahertz NMR costs about 800,000. The 400 that's shown in the middle probably cost about $500,000. 900 megahertz NMR is upwards of 5 million these days, and 1020 that's shown on the right took 20 plus years to develop and cost multiple millions of dollars. Now they have recently developed a 1200 megahertz instrument, and it's going to cost about 15 million for anybody that would end up buying that. The stronger magnets will cause nuclei to respond to much higher frequencies, and so they can be much more resolved. We can tell a lot more about a molecule, but it's really not necessary for most of our small organic molecules where we only have a couple of protons anyway. Most of the larger instruments are actually used by biologists to do DNA, RNA, or protein structure. So we know that our NMR is going to have some reference frequency. So for our instrument, 60 megahertz is the reference peak that we would use for our protons. That reference peak is compared to all other peaks, and we talk about the amount of shielding that reference peak has, indicating how much any individual proton that we're looking at might move from that reference peak. And so, for example, you are pretty familiar with how sunglasses work. You get more signal, you get more energy from the sun if the sun hits your eye directly, but if it hits sunglasses, then you're shielded, you feel less of that intensity. So we know that we're going to have some magnetic field that's external, but if we have electrons that are sitting around any individual nucleus, those electrons can actually generate a magnetic field too. If you have a place that electrons can move and a magnetic field, the magnetic field will cause electrons to start to move in a circle. It's something that you'll learn about in physics too. Typically, those electrons will move according to the right-hand rule. And so we'll see the electrons start to cycle around that external magnetic field, and then we'll end up generating a reverse field in opposition to the original magnetic field. So the magnetic field that's actually felt by any nucleus is both the external magnetic field and then whatever's going on locally around an individual nucleus. So we call the effective magnetic field, it's the sum of the external field and whatever happens locally. That's what we actually are going to measure the frequency of. So we could have this shielding factor a lot of different ways. So right now we have a reference shield. That local magnetic field is going to depend on both the inductive effect of electron withdrawing groups, right? That's saying how much we're going to draw away from a given nucleus based on how close and how electronegative something is, and also something called magnetic anisotropy that we're going to talk about in a little bit. So if we're looking at a smaller electron density because we have something like a chlorine or a bromine or an oxygen nearby, we would end up having less electron density around a nucleus. That means that magnetic field will generate less electron current around in the orbital. And when it generates less electron current, it will generate a smaller reverse magnetic field. And so we end up with a higher effective magnetic field for that nucleus. Magnetic anisotropy typically will give us more negative values for B local and a greater B effective. It works like this. We have a large area, usually from lots of p orbitals that are lined up, like in an aromatic system, and that can generate a really large ring current. When it has that large ring current, we're actually feeling often the hydrogens on the outside of the aromatic, and so we're actually increasing the amount of local magnetic field we give. So here's our first example of what an NMR spectra actually looks like. There are a lot of things to look for on an NMR spectrum, but the very first thing that we want to see is how many different types of environments do we actually have? How many different types of protons do we have? Anytime that we have atoms that feel identical chemical environments, right, they're attached to the same things, they're going to give us identical signals. We call all of those homotopic atoms, meaning they have the same environment, homosame. So here we have the structure of benzene and the NMR of benzene. Benzene has exactly one peak relative to a reference. We see how much it shifted relative to that reference. And it only has one peak, even though it has 6 protons, because every one of those protons is exactly the same. Now, if we look at this molecule has 2 different protons, one that's on the carboxylic acid and the other that's on the alkyne. The carboxylic acid peak gives us one signal. The one that's on the alkyne gives us a different signal. Because they both feel different environments, we call them heterotopic atoms. The number of heterotopic atoms is going to determine the number of signals. Notice that we have the 2 signals, and then we also have a reference peak that's at 0. That's so we always know where we're having that 60 megahertz signal or whatever other the reference signal happens to be. Some of you might be able to intuitively tell which types of hydrogens are different. A lot of our nomenclature and stereochemistry arguments have built us up with some of those skills, but we can do this systematically as well. So if you want to know what types of atoms are homotopic or which types are heterotopic, one of the ways that we can do that systematically is called the chemical distinction test. So anytime you're curious about an atom and saying, is this actually the same as other atoms, we can draw the structure of everything the same except for the atom that we're looking at and just label it as an X or a halogen. I like to use bromine. Then we say, we're going to determine which molecules are identical or enantiomers. Any of the things that are identical or enantiomers are going to be called homotopic because they are chemically equivalent. If the X being at different locations gives us the same name or the same molecule, we know that it's actually the same as all the other hydrogens that we're trying to replace. After we've determined which ones are homotopic, we also try to figure out which ones actually are constitutional isomers. They give us different names, and these are heterotopic. These are chemically distinct. And so we'd say if we have different names for the molecules, we would end up having those count as separate signals. The number of chemically distinct atoms is always going to determine the number of NMR signals. It's the same thing that we said last time. So we're always looking for how many things are different. So let's do this together to see what that test looks like. So here's a chemical distinction test. We took this 2-methylpropane and we switched out every one of the hydrogen positions with a bromine. So if we switch out the hydrogens that are on the leftmost carbon, we end up with this molecule right here, which is a 1-bromo-2-methylpropane, or we might have another 1-bromo-2-methylpropane, or we might have another 1-bromo-2-methylpropane. Since every one of these is 1-bromo-2-methylpropane, we know that each one of those hydrogens that we replaced there are homotopic. They are not distinct. Now we could also replace the hydrogen that's on the center atom. If we replace the hydrogen on the center atom, we end up with this molecule, which is a 2-bromo-2-methylpropane. Because we end up with a different name, a different structure, a different molecule when we replace that hydrogen with a halogen, we know that hydrogen is different from all the others. So we'd end up with 2 signals from this. We could try to do the same type of chemical distinction test on this toluene. So why don't you go through and try to identify where there are hydrogens on this molecule and what 4 different molecules we could make if we replace the hydrogens with a halogen. I used bromine. I'll use bromine again when I go over this with you. So these are the 4 different molecules we could make. We could replace the hydrogens on this position, there are 3 of them here, to make a bromomethylbenzene that we see here. Those 3 hydrogens mean that we should see a signal for 3 hydrogens there. We could also replace the hydrogens that are on this carbon or this carbon. Those are both ortho positions to that toluene, and so we end up with orthobromotoluene on both of those. That means that signal should have 2 hydrogens associated with it. We could also replace the meta position hydrogens and end up with metabromotoluene. And again, we'd see 2 hydrogens associated with that signal. And finally, we'd have parabromotoluene from replacing this para position. And there's only 1 para position, and so we only see 1 hydrogen for that. If the only difference is at a single stereocenter, like if we're making 2 different enantiomers of the same molecule by replacing a hydrogen, then we will end up with things that are still homotopic or still chemically distinct. So like in this case with the bromobutane, if we replaced with a chlorine here or a chlorine here, we'd have both the R and S versions of this molecule. But because that's the only stereocenter, we consider those equivalent anyway. We'd also consider things equivalent if we could rotate around and end up with the same molecule. So we see here HC and HD might look like they're not mirror images of each other, but if we just turn the molecule around, HD is where HC used to be and HC is where HD used to be. So they're still the same. We know that in chapter 4 we also talked about conformational isomers. If we replace a hydrogen with a halogen and the only difference is a rotation, we know that those rotations can happen. And because those rotations actually happen really quickly on the scale of the timeline that we're measuring NMR with, all of those signals get averaged together. So even though there are 3 protons on acetic acid's leftmost carbon here, every one of those 3 protons can be interconverted to the other ones through rotation, and so every one of them will have the same average signal. So we can see that fairly clearly if we look at the actual spectrum. We have 2 heterotopic protons, one from the carboxylic acid and the other from the CH3 group. The CH3 group is on the right and the carboxylic acid is on the left. We only see 1 peak for that CH3 group because every one of those hydrogens are turning around and averaging together. We can see the same type of thing in chair flips. So the hydrogens that are axial and equatorial in a chair usually actually give us the same signal because that chair flip will happen back and forth in the timeline that we're taking the NMR. So far, we've mostly talked about the number of peaks that we'd actually see from an NMR based on the heterotopic atoms. That's the first thing that we need to be able to see from an NMR. The other thing that we want to be able to identify, or one of the other things, is where those peaks actually are. We call this chemical shift. So the chemical shift is going to be the frequency of our sample minus the frequency that we see for a reference peak, which is almost always tetramethylsilane or TMS. And we're going to divide that frequency by the optimum frequency, which is again that TMS signal, and we're going to multiply that by 10 to the 6. So we're essentially saying that out of 1,000,000 possible frequencies, how much are we shifted over? We always do it this way because when we measure it this way, the shift that we get is going to be independent of the instrument strength. So we can look at the same spectrum from a 300 megahertz NMR on the top, an 80 megahertz instrument below that, a 60 megahertz instrument below that, and a 42.5 megahertz instrument below that. The shifts that we see for each of these are going to be exactly the same. We're going to report them as parts per million and they all line up. So you can see that in this column on the left, we have all of these peaks lining up. We do see a change in the structure of those peaks. These peaks are actually all resolved a little bit better. They all show up in the same location, but it's easier to read the topmost spectrum. And we see the same thing for this set of peaks. The top is easier to read because it's a higher resolution instrument, but it's not in a different location. We see the same thing in these peaks. These peaks start to blur together in the lower ones, but these 2 peaks are in the same place all the way down, even though they're blurred in the lower ones. And again, we see these 2 peaks that are on the top now blurred together below, but still in the same location. So because we normalize this way as parts per million, it does not matter what instrument we have, the shift is always going to be the same. We have some language that we always use when we talk about shift. That shift is always going to be referenced to a TMS, tetramethylsilane, reference peak in the NMR spectrum. So that should show up at 0. The greater the shift actually shows up on the left, which is kind of counterintuitive, but this is the way they always are. So more shift would represent something that has a lot of electron density pulled away from it. We say that it's downfield and we say that it's more deshielded. So notice when we have a hydrogen on an oxygen in this acetic acid, the oxygen is pulling a lot of the electron density away from the hydrogen. And so that hydrogen doesn't have very much to block the magnetic field from it. And so we see a much larger shift. We say it's more deshielded. Now, on the right, the carbon shares its electrons much more easily with the hydrogen. And so we see the CH3 group, every one of those H's is much less shifted. It's a lot closer to TMS because it has a lot more electron density around each hydrogen, and it's blocked more from the magnetic field. Practically speaking, we're always going to use chemical shift tables to give us a reference for what types of peaks we might be looking at. We don't have to come up with these on our own. And so this is the shift table from your book. There are a couple of things to note in each shift table. First of all, I want you to think about what happens when we increase substitution. So if we have more carbons attached to a hydrogen, we generally see that chemical shift go up. That's because carbons are more electronegative than hydrogen. So if we're replacing H, like we see in 2, with a carbon, we would expect that carbon to draw a little bit more of the electron density from the neighboring hydrogens, and so we see that shift go up. Now, it only goes up a little bit. Notice all of these are relatively lowly shifted. Another trend that I want you to see is what happens when we change the electronegativity of a group, but not the number of substitutions. So if we look at bromine attached to a carbon and then what happens to those hydrogens, a single bromine is going to pull a lot of electron density away from that carbon, and that carbon will then pull more electron density away from the hydrogen in turn. If the bromine pulls more, the carbon has less, so then it wants more from the hydrogen. So we see a pretty significant shift from that bromine being on there. But because chlorine is higher on the periodic table, it's actually more electronegative, and we see a greater shift. So go up from the 2.7 to the 3.1. Oxygen is more electronegative still than chlorine, and so we see an even greater shift when we have an oxygen on a carbon. We can see a similar type of shift between oxygen and nitrogen. Oxygen's more shifted than nitrogen, right, because oxygen is more electronegative. But the other thing that I want you to notice is that these have much less defined chemical shifts whenever we have an NH or an OH. And that's because both NHs and OHs can hydrogen bond between molecules. And so we see an average shift in the same way that we saw an average shift for the IR signals. The last types of differences that we see are when we have alkynes and aromatics. This is also true of alkenes. We actually see much more significant shifts than what we would otherwise expect for just the atoms that are connected. And that has to do with the p orbitals and how electrons can flow through the p orbitals. This is the same shift table that we looked at before. It's just broken up into 2 pieces so you can see it more easily. We see the bottom half of that sequence of bromine, and then chlorine, and then oxygen. Fluorine ends up shifting much more. You can see that number 12. And again, that makes sense because fluorine's more electronegative. We can also see shifts corresponding to groups that are near carbonyls. We see pretty significant shifts because the carbonyls, the double bonds to oxygens, pull a lot of electron density away. And we also again see on the right, when we have OHs, a much wider range because of the ability to hydrogen bond between molecules. Just to make sure that we hit this home, right? The 2 main ways that we see differences in shifts are inductive effects and magnetic anisotropy. So inductive effects come from electron withdrawing atoms that are nearby. And so we saw that in this trend, 9, 10, and 11. Bromine is less electronegative than chlorine, and so it shifts less. Oxygen is more electronegative than chlorine, and so it shifts more. The larger the shift is always, in these cases, from different electronegativities coming from the most electronegative atoms. We say that because the electronegative atoms pull that electron density away, it de-shields the neighbor hydrogens, and we end up with a much higher frequency shift and a larger chemical shift. Again, the extent of this inductive de-shielding depends on the electronegativity of the nearby atoms. We talked about this briefly before, but again, the second factor that affects the shift is magnetic anisotropy. So here's an example of benzene. Benzene has a large system of p orbitals that are all talking together. That's why it's aromatic. So the molecular orbitals aren't just on one spot. Because of that, we can actually move electrons around a much larger ring. And that allows us to have a much larger current responding to the magnetic field. When we have that current, the opposing part is actually in the center of that ring, which we can see in the diagram on the bottom right. And the part that actually is increasing the magnetic field is right where the hydrogens are. So the hydrogens are feeling more external magnetic field because they're having that magnetic field amplified by the ring current. We can have the same type of anisotropy in alkenes. So alkenes have a large P system, not nearly as large as the rings, but it's still there. And that ring current can generate a larger response to the magnetic fields. And again, the hydrogens are on the outside of that magnetic field, or the current generated by that magnetic field. And so we actually see an increase in magnetic field, which means that when we have alkenes, even though the carbons aren't more electronegative, we see a much larger shift than we see with alkanes. Because of the geometry of alkynes, we actually see kind of an opposite effect from anisotropy in the alkynes. The alkynes can move electrons around through all of the p orbitals that are around an alkyne, which we can see on the left. As we generate that current, we generate a magnetic field that actually opposes the alkyne protons from that current. And so we'd see the hydrogens associated with the alkynes, if they're directly on those carbons, actually feel less magnetic field. And so they're much less deshielded than we saw with the alkene hydrogens, and so we actually see less shift than we otherwise would expect. Annulenes are aromatics that are larger than six members, usually all carbons. So here's an example of an aromatic molecule. It has p orbitals all the way around. It can have a ring current that goes all the way around. Unlike benzene, though, it has protons that are both on the outside that will have an increased magnetic field, and we actually have some protons that are on the inside as well. Those protons on the inside actually feel less magnetic field rather than an increased magnetic field. And because this ring is so big, we can generate a lot of current, and they can actually be a lot less than we'd expect. So these actually show up as negative shifts to the right of TMS. So it's important when you're dealing with complex systems to understand at least the basics of how this works, because normally you don't even scan in that range because you don't expect to see anything that's shifted negatively. I want to make sure that we're all on kind of the same page about what you should have at the end of this lecture. You should have a general idea of how NMR works, just a basic background. You should also be able to identify the number of NMR signals given off by a certain molecule, right? So based on the number of heterotopic protons. And we should be able to use a shift table to identify the approximate locations of the shift. So if we see something that's attached to bromine, we look at the shift table, say, oh, it's going to shift more. We should also be able to explain the shifts in terms of the inductive effects, so what's causing the shifts, and also magnetic anisotropy. So either attached to something electronegative or has a ring current. That's it.